Welcome to the Explainer. Today, we're going to tackle a subject that, let's be honest, has a bit of a scary reputation: calculus. But what if I told you that it's really just about two big ideas? And not only that, but you probably already get them on a gut level. So let's break it down. So forget math for a second. Let's start with something you've definitely seen: a car's dashboard. Because you already understand the two core ideas of calculus just by looking at it. Your speedometer, right? It gives you a snapshot, your speed at one single moment. That's what we call an instantaneous measurement. But then you have the odometer. That gives you the big picture, the total distance you've traveled since the car was new. That's an accumulated measurement. Okay, just hang on to those two ideas: a snapshot versus the complete story. Because really, that's it. At its heart, calculus was invented to answer two huge questions about how the world works. And you're going to see these questions map perfectly onto those two gauges on our car dashboard. These two questions, this is the key to the whole thing. The first one: how fast right now? Well, that's our speedometer question. And in calculus, that leads us to this thing called a derivative. The second one: how much has built up over time? That's our odometer question. And that leads us to the integral. And that's it. Those are the two big pillars we're going to explore. Okay, so if we're going to talk about change, we need a way to describe it properly. We need to speak the right language. And for that, mathematicians use a super powerful tool called functions. Just think of a function like a little machine. You put a number, let's call it x, into the machine. The function has a rule, like multiply it by 2 and then add 3, and it spits out a new number, y. That's all it is. Functions are just the language we use to describe these patterns of change. All right, so let's put this language to work. We're going to tackle that first big question, the speedometer question. How fast right now? And we're going to do that with the idea of a derivative. To really get the feel for this, let's forget numbers again for just a second. I want you to just picture a simple rolling hill. Now, finding the average slope between 2 points on this hill is pretty easy, right? You just see how much you went up versus how much you went over. But what if you wanted to know the exact steepness right where you're standing, at one single tiny precise point? Now that is a much harder question to answer. And this is exactly where the derivative comes in. It's the mathematical tool that lets us answer that tricky question. It's like having a magical magnifying glass that lets us zoom in infinitely close to one single point on a curve and find its exact instantaneous steepness. And here's where you really see the magic of calculus. The long cut on the left, that's the formal idea. You calculate the slope between 2 points, and then you do this whole process of mathematically shrinking the distance between them to 0. And it works, but it's slow. The absolute genius of calculus is that it gives us these beautiful shortcuts, like the power rule on the right. It's a simple rule that just gives you the answer instantly. We're not going to get into the weeds of the rule itself, but it's a perfect example of how calculus makes really hard problems easy. Okay, so we've seen how derivatives let us break things down into these tiny snapshots of change. Now let's flip it. Let's tackle our second big question, the odometer question, and figure out how we put all those little moments back together. The big idea behind this, which we call integration, is just as easy to picture. So imagine I give you this weird curvy shape, and I ask you to find its area. How would you even start? Well, a really smart way to get close would be to fill it up with a ton of tiny, simple rectangles. Because you know how to find the area of a rectangle, right? And the integral, well, that's the tool that makes this whole process perfect. It's what lets us add up an infinite number of these impossibly thin rectangles to get the exact total area. It's how we find the total accumulation, the whole story. Okay, this is the moment. This is where it all clicks into place. Because these two big ideas we've been talking about, taking a snapshot of change and summing up the total change, they are not separate things at all. In fact, they have this deep, beautiful, inverse relationship. They're two sides of the same coin. Check this out. It's kind of like a little puzzle. If we take the derivative of x squared, we get 2x. Okay, but if we take the derivative of x squared plus 5, we also get 2x. And the derivative of x squared minus 7 is also 2x. See what's happening? All these different starting points give us the exact same derivative. Kind of weird, right? So that leads to a really fascinating question. What if we try to work backwards? If all we know is the answer, the rate of change, the derivative, is 2x, can we know for sure what the original function was? And the answer is, well, no, not perfectly. we get a whole family of possible answers. We know the original function had to have an x squared in it, but we have no idea if there was a constant number tacked on the end, because the derivative of any plain number is just 0, it vanishes. So we represent that mystery number with a plus c. So here is the crucial point, the main takeaway. The derivative and the integral are perfect opposites. The derivative breaks a function down into its tiny moments of change. The integral takes all those moments of change and builds them back up to find the total. One undoes the other perfectly. And this incredible connection, this idea that breaking things apart and putting them back together are inverse operations, that's not just some neat party trick. It's called the fundamental theorem of calculus, and it's celebrated as one of the most important and powerful ideas in the history of mathematics. It's what makes the whole thing work. Okay, so this is all very cool, very elegant math, but why should you care? What can you actually do with any of this? Let's look at a really clear example of why this all matters. This little table says it all. Velocity, your speed, is just the rate of change of your position. So if you know where an object is over time, the derivative tells you its velocity at any instant. And going the other way, if you know an object's velocity over a period of time and you want to know how far it traveled, you just take the integral. Calculus becomes this amazing translator between rates and totals. So as you start playing around with these ideas, here are just a few little traps people fall into. First, don't forget that plus c when you integrate. Second, make sure you know if you're talking about an average rate of change over a long time or the instantaneous rate at one specific moment. And finally, just take a breath and make sure the problem is asking you to break something down with a derivative or build it up with an integral. Because in the end, calculus isn't just a subject you learn in school. It's a completely new way of thinking. It's a lens that lets you understand the world in a deeper way, from the path of a planet to how your investments might grow to how a disease spreads. It is, quite literally, the language of change. And now you've got the basics of how to speak it.